Today I think we have 5 classes, yeah, if I count properly. So great to see you here. As you can see, today we will continue the topic of ordinary differential equations, and I hope that we'll continue with nonlinear solving of nonlinear equations as well. Yeah. Last week about all these we discussed, if I recall correctly, about Euler's method. Yeah, the famous forward Euler method that we derive based on just basic principles from the calculus. Yeah, and it works well at least for our solution for population growth. Yeah. Next, we continue to analyzing the system of mass spring damper. In practice, it was mass spring system. Yeah, but as I recall correctly, we just derived it and haven't solved it. So we'll start with solving it. And yeah, and I think that's mostly that. Yeah. I get another email. So yeah, so this year community students is pretty active at least in emails. Yeah, so I get another email that with complaint, correct one, that that some of the codes that we discuss here, especially that the one that we skipped, yeah, are not really then shared on Moodle. Yeah, so I will fix it. Yeah. So I will put after today's classes more relevant code, especially for ODEs, nonlinear equations, and I think that maybe also for the one that want to trace back for those numerical integration. Yeah, we'll also have today assignment. Yeah, that will combine a little of those one task from numerical integration and 2 tasks from ODE. About the task for nonlinear equations, I think it will be already combined with some stuff with solution for mechanical systems. Yeah, but let's see how it will develop. Yeah, I think that today we won't close nonlinear solution for nonlinear equation, which is pretty fine. Yeah. Most likely next 2 weeks will be the lecture will be delivered by my colleague Alexander, as we discussed last time. Yeah, but let's see. Yeah, because the issue is that in any few weeks we have a trip. Yeah, so I think that he will come. Yeah, if it will change, yeah, then I will of course let you know. Okay. Any questions, remarks, complaints, or can we continue with the topic? Okay, perfect. Alexander also give me a hint. Yeah, okay, it's not related to forward Euler. Yeah, that I should, collect some of your, let's say, insight from the students anonymously. Yeah, but I haven't prepared for today, but maybe for next time. Yeah, some kind of poll. Yeah, in one of those another fancy systems like there are the one I don't remember the names. Yeah, but yeah, let's see how it'll go. Maybe even Socrates supports it. But okay. So this as a reminder, what we were discussing last time, yeah. So we were discussing about forward Euler, yeah. So after few internal Hero's algorithm, yeah. So Hero's algorithm with the forward Euler scheme, yeah, that it progresses with time based on the previous time, yeah. So it also shows that this is explicit method, yeah. Do you know what is the difference between explicit and implicit methods? You know these? Yeah. So just a reminder, yeah. So for the explicit method, yeah, like here, you can calculate the next step based on the values from the previous steps, yeah. Let's laser pointer, yeah. Which is pretty convenient, yeah, because then you can just calculate it like that. And for the implicit methods, yeah, and for example, backward Euler is example of the implicit method, yeah. Then terms for the next time step appears on both ends of both sides of the equation, left side and right side, yeah. And then what we do in this case? In this case, when you have, unknowns on both sides, then you have set of nonlinear equations, and then you have to use solver for nonlinear equations that we'll learn later to solve this kind of the task. Yeah, we'll discuss this a little later. But okay, this was about what was last time. Yeah, and then we analyze the code that solves it and write some test for it. Yeah. Next was about this type of the system, spring damper system. Yeah. So spring damper system without, firstly, as you can see here, there is also, spring and mass constant. Yeah. So mass spring system, not damper. Yeah. So damping for this case is equal to 0. Yeah. And also we have no external excitation. Yeah. And this, thanks to this, we also get pretty straightforward solution for this kind of the system. Yeah. So I think that this is the easiest, second order system that we deal with. And now we want to solve it. Yeah. So again, we discussed last time how we can use forward Euler method that was designed to solve first order systems to apply to second order system. Yeah. So we discussed it, yeah, and we came out with this set of equations. Do you remember the discussion? Yeah. So this is the equivalent system written. So instead of one equation for second order, we have two equations for the first order. Pretty standard, yeah, approach. Yeah, it always works like that. And here we can see how the forward Euler method can be applied to those two equations. Yeah. And then for the 1D system, yeah, we have this kind of equations, simply like that. Yeah. So after transforming, yeah, those are just equations. We have two of them now. One provides a solution for the position, yeah, and the second one provides a solution for the velocity, yeah. That solves the system of mass spring system without external oscillations and without damping using forward Euler. Okay, and then we can compare it with exact solution. Yeah, nothing fancy here. So how we should solve it? Do you want to solve it? Do you want to solve it together or just show your solution? That site never said anything, and so I suppose that it will stay that way. I mean, the online site, yeah. So it's only up to you. Of course, if you have anything to add, please add. Maybe we can solve it together. And the reason is that it seems that this coding part still is pretty challenging to some of you. Yeah. Which I understand. So let's try. I think that here I even have it solved. Yeah. Mass spring with 4 Euler. So if something will, we won't work out, we can. Or okay. Or do you see no difference if you write the code or analyze the code?
Slowly writing this better. Slowly go for it. So we can see less overwhelming.
Yeah. Okay. Let's try. If we'll be able to solve it. Yeah. So let's start with mass spring using forward Euler version 2. Yeah. So version for today. So empty script. So I will put it in the full. Yeah. Put it somehow aside here. Yeah. Okay. And here we have those equations. Yeah. So so not to start from the very start, I will open forward Euler and copy this part. To have some base, because I'm not so fond of calculating all those initial stuff from the scratch. Yeah. So let's start by defining the system. We have omega 0. Omega 0 is provided, is 2. Yeah. And we have x0 equal to also 2. Because our end time and dt are as a function of t0, yeah, so oscillation period. So let's calculate t0, 2 times pi by omega 0. So this should be in seconds. And now we can take this part. So this is base for this information. Yeah. So dt is equal to t0 by 20, and t is equal to, let's name it as it written here, 3 times t0. Okay, up to now I suppose there is no much question. This is this pretty standard initialization phase, yeah. So we just in practice rewrite everything that's here, yeah. So to set up the scene. And I brought this code to use this part. Because I always have tendency to forget what is exactly, how should this indexing work. So it will save us some of the debugging. So I will add here +1, yeah, because then this is the total number of the steps, including initial condition. So now we can okay, just like that. So U is this kind of the vector. And then aside of U, of course, we have to store somewhere V, so our velocities. So it is the same, yeah. So this is initialization to provide, the space for position and velocity. Time can be the same, okay, yeah. So time vector. It is written, by the way, on purpose. It's nt times dt. So because I changed it, it should be nt -1 times dt. Do you know why here we have nt times dt instead of having tk? Is there any difference? There is. And it's minor one, but it's again, it's one of those minor detail that can make a difference. Yeah. So everything works well, and it doesn't really matter how do you write it until tk is divided by dt. Okay, because then but here you have floor. What is floor?
Like
Yeah. Yeah, exactly. Yeah, here it's floor. Yeah, so it's one of the rounding methods. Yeah, so it's here to get this as integer, because it can easily happen that you choose tk and dt that are not fully compatible. Yeah, that provides you, some small offset. Yeah. So here it's written in the way that this doesn't necessarily must equal exactly to tk. Yeah. So it will be the closest value to tk, the possible, yeah, to according to time step. Yeah. But it can differ slightly. Yeah. So if you provide that, for example, we have, like, for example, 0.1, yeah, and we have 1.03, yeah, time end, it will, and it won't, integrate to 1.03, but to just to 1, because it will be, we will provide 10 time steps forward in time. Okay. Makes sense? Because then if we put here the tk and still march with dt, then it may happen simply that, those t and u won't be compatible. Yeah. So another source for very nuanced errors. But okay. I hope this is understandable. Yeah. So, and now I don't remember if this is exactly written here. Yeah. But we'll solve it by setting u as x0, yeah, because x0 is our initial displacement, and we will set v of 1 equal to 0. Yeah. So this is, and maybe we will group it. Yeah. So this part is problem definition. So this is kind of problem definition, yeah. So this is preparation for solution, yeah. So to initial variables and calculate some constant values, yeah. This part is initial conditions, yeah. So those are initial conditions, yeah. So we set displacements according to definition, and we set 0 initial velocity, yeah. And
B0, if we only have omega 2 red. Omega 0, like omega 0 is 2.
Yeah.
We have some kind of initial something.
Initial something.
Yes, initial velocity.
Why?
Because omega 0 is 2.
It's not related. Okay, so I understand that this can be okay. So omega 0 is just property of the system. Okay, it's natural frequency, natural this frequency or algorithm velocity. Yeah, so it's not kind of state of the system, it's characteristic of the system. Okay. So this is the frequency on which system is expected to oscillate. So it's characteristic. Yeah. And now we are talking about excitation. Yeah. So it's not connected. Yeah. At least not directly. Of course, this omega 0 defines exactly how the system will evolve in time. Yeah. And that's why we're expecting to have this kind of the property like oscillation period that is based on it. But again, this is characteristic of the system. Make sense? Yeah. So based on omega, we are expecting that, we will see 3 full cycles of oscillations. Yeah. But we can start at any initial condition because those are totally independent values. Okay. And now we are ready to implement equations. Okay, now I know why it's written that way. Yeah. But okay. Next thing is always tricky. So okay, so you, yeah. Okay, now we can see everything. So u n plus 1, here we are just working with the vector, so we will remove it, is equal to un plus dt vn. Yeah. So here we will just write vn as it's shown here. Yeah. And the second equation is simply vn plus 1 is equal to vn minus dt times omega 0 squared times un. Okay, and that's all. And of course, this minus comes from the equations directly. Yeah, when you're deriving equations and then putting them on the one side and then applying forward Euler to it, we get with this set of equations. Yeah, so this is the special case that defines to us uh, mass spring system. Okay, make sense? Any questions? No. Okay. So now we can of course plot it. Plot TU. And let's see if it runs at all. Okay, we got something. Does it look nice? Yeah, but does it make sense? No, it doesn't make sense. Why it doesn't make sense?
Advice.
Okay, I cannot hear you super well, but I think that I get some of those keywords, and you're right. Yeah, it shows like the system is unstable because this is simple mass spring system, and there is totally no reason for it to increase its vibration. Yeah, because it's conservative system, and here we can see that oscillations, because we plot in time amplitude increases, so something is wrong. Yeah, so uh, to be sure, yeah, we can calculate also exact solution. Yeah, so here we can uh, wait with this plot and calculate exact solution. Yeah, so plot t u t, and here we have xo xo times cosine of omega o times t. Okay, it's not super nice. Yeah, so you let's put it in a nicer way. At least I prefer it that way strongly. So then we know what is happening. Yeah, and then I would also add X label, even very short description. So on the X we have time, and on one Y we have what we have U. So we have the displacements in meters. Yeah. And finally, let's add some legend. Yeah. So first one is miracle, and the second one is an okay. And make it bolder. Okay. So, well, now we can see, even more obviously, and that, of course, it's not a surprise, yeah, that this is the behavior. And the question is why this is the case and how we can solve it. And should we be worried about this? However, I can see that I could prepare also some quiz here. So let's get to, okay. Oh, there's even some comments. Okay. Someone, if you have any remarks, you have to unmute because this is, I believe, the only way that I can hear you for sure. Okay. So let's back to this one. Okay, so this is a little annoying. Because I prepared those quizzes thematic, yeah. So firstly we end up with those ODs and then we'll switch to nonlinear equations if we reach this topic. But okay. So I I have to do this next time different way because it's even okay. But here you have the correct question. Yeah, the room is the same. So let's see how it will work. Yeah. So why does the forward Euler method often fail to produce accurate results when applied to simulate oscillating systems such as the simple harmonic oscillator? Yeah. So the simple harmonic oscillator is our example. Yeah. Okay. People are still on. Let's give 15 seconds. Yeah. But I think that it's pretty obvious what is the correct answer. Hopefully. Yeah. The forward Euler method cannot handle second order differential equations. It can because it means that we wouldn't be able to solve it at all. Yeah. And we were able to solve it. Yeah. That just doesn't provide correct answer. Yeah. But it can handle second order systems. Yeah. As you can see here. Yeah. So as it was explained here, yeah. It's not the best method to solve this kind of the system, and it's known that it introduces some instabilities, like it's shown here. Yeah, so it doesn't work super well. Yeah. Uh, so yeah, as it result doesn't look promising. Yeah, we can verify the implementation. For our inputs, we should have at 1 step second. Yeah. Okay. Yeah. We can check it. by so slides, yeah, and Matlab. We can check it simply in here, yeah. So we can check what is value of u of 1. I think it was more about second. Assuming that we are counting from 0, yeah. So this, because it doesn't make sense, then this is for initial condition, because initial velocity was 0, yeah. So u2 agrees, yeah, and u2 of course doesn't change because velocity was 0, so position at second step has to be 2, yeah. So let's see what is v of 2. It's pretty correct. To see it more clearly, we can see it with 706. Okay, so our implementation looks reasonable, at least. So let's check the next one. 1.8026079, yeah. And then we can also calculate u of 3 minus 2513. Okay, this looks pretty okay. So let's check this with reduced time steps. Yeah. So what will happen if we reduce time steps? Yeah. So here we have plot for dt equal to t0 by 20. Yeah. What will happen if we reduce it to 40? So we open a new figure and let's run the code. Okay, so it organizes everything in this way, and still you have to do everything by hand. But okay, yeah. So here we have so here we have by two t0 by 20. Yeah, here is from the time step t0 by 40. Next one should be 160. So let's open a new figure. Let's put it somewhere here. And let's run the code. Okay, it looks much better. And then let's go to 2000. Open new figure. Put it here. And leave it here. Yeah. I don't really understand what is this new icon, but it appears here. But okay. So as expected, yeah. So when we decrease the numerical time step, method behaves properly. Yeah. So as you can see, just with like, I think, so we have T0 by 2000. So here we have just 6000 time steps. Yeah. So by the way, what is our DT here? For the last one is like 1.5 millisecond. Okay. So here we have the time step of 1.5 millisecond. And for this time step of 1.5 millisecond, we can see that the error is small. Yeah. We can see some difference here, but it's relatively small. So is it okay or not?
See, it starts already oscillating again.
Yeah, but so method behaves pretty okay. Yeah, it solves the system, but it's for sure not the solution that we want to get, because here we have like time step of 1.5 millisecond. Yeah, and this is not acceptable for something that oscillates at the rate of 2 radians per second. Yeah. So for this kind of the system that it's pretty slow, yeah, we should also be able to solve it with much larger time step. Yeah. So why it works, yeah, we have to decrease the time step to some unreasonably, small amounts. So in any case, we can get some reasonable solution with this four-out Euler, but it doesn't behave at all correctly for the simple system like this mass spring system. We have to find a better solution. So let's close all those windows here. Let's make it full screen. So yeah, the results start looking correct, but it's not something that we want to have. Yeah. So there is a magic fix to this method. Okay. So clearly, four-out Euler is not effective. We have to reduce the system to very small ones. Yeah. And yeah. So now we will makes a very small change. Yeah. So let's have this code. Yeah. So I will copy paste our code that we have just written. Yeah. Change in name to fix v2. Yeah. We won't use the old one. It seems that the new one works perfectly fine. Yeah. And we will here on the file names we fix, we will fix it. Yeah. According to this idea. So now we will use un plus 1 instead of un for the second equation. Yeah. So here we have the second equation. And here, instead of using un, we will use un plus 1. Okay? Yeah. So, yeah. So we simply add here un plus 1. And this is valid because simply it's available. Yeah. So kind of it changes the part of our scheme to x implicit 1. Because, for the second equation, like this equation, we have the values that correspond to the next time step at both sides. Yeah. But from other perspective, we have already calculated it. Yeah. So let's see how it behaves. And let's decrease the time step to the original one. Yeah. And let's see if there's it's anyhow better. Yeah. And now again, I have decreased the time step to original value of t0 by 20. Yeah. So dt is 0.15 seconds. Yeah. So it's quite far from 1.5 millisecond area. Yeah. As you can see, we decrease the time step like 1,000 times, yeah, 100 times, sorry. And still, you can see some shift here, yeah. I think it's especially by this initialization, yeah. But it preserves the characteristic of the system much better, yeah. So, and if we just change it to, for example, t0 by 40, which was the second value that, as you might remember, still bring very poor results, yeah. Here the results looks much better. Yeah. So as you can see, it preserved the characteristic of the system very well. Yeah. So what does it mean? It means at least the selection of the correct integration scheme is pretty important. Yeah. So what we have done. Yeah. So new schemes gives far better results. We just have seen it on our numerical example, and what has happened. Yeah. So instead of using the old scheme, yeah, we have the new scheme that has here an n plus 1. Yeah, so we take advantage of the case in the code that we have this already calculated here, and we can use it here. Yeah, so firstly, you can see that we have added some new information. So first equation forms a forward difference, as is done in four-out Euler. Yeah, so there is kind of no brainer here and no change here. Yeah, so we base it on forward difference and form forward Euler. We preserve it, so nothing has changed here. And however, as you can see, the second one is evaluated, this part, at Tn plus 1. Yeah. So due to Un plus 1. And it means that we transform this to backward difference. Because you can see already that, again, this is explicit scheme. This is explicit scheme. This is implicit scheme. Yeah. And we change it to forward difference, to backward difference. Yeah. So do you know what is different between, do I have plot here? Oh yeah, I have it here. Between backward and forward difference? Yeah, exactly. Because well, this is nothing super fancy, to be sure that it's understandable. Yeah. So simply we moved from here to here. Yeah. So forward difference simply calculates value at this time, okay, using this and the next time step. That's why it's called forward difference, yeah, because it uses the current point and the point forward in time, yeah. Backward difference calculate this value by using this point and point back in time, yeah. Of course, they are at the limit, both of them are equivalent, okay. Yeah, so there is nothing magical here. Yeah, if we get to this point in limit, we will get the tangent. Yeah. The same like we get this point to put here and we get the tangent. Yeah. The difference is that forward difference method provides us with explicit integration scheme, and backward difference method provides us with implicit integration schemes. And implicit integration schemes have tendency to be more stable, because they require some iteration, because they have information about the future on both sides. Yeah. Yeah. By the way, the scheme that uses backward difference is often called backward Euler. As we have here forward Euler with forward difference, backward Euler with backward difference. Yeah. Backward Euler, okay, we are not here to prove it. Yeah. So there are much smarter guys that has proven in their book. But if you're interested, I can give you the literature about the integration. It's an interesting topic. Backward Euler has better stability properties, but it is implicit method. Yeah. An implicit solution for implicit method is far more involving than explicit method. However, we have here mixed method. Yeah, the standard way to express the scheme is to apply forward difference. Okay, so it's about okay, so here it is about let's say how it is done typically. Yeah, so just the order of equations is typically reverse when you find it in literature, but it doesn't show the characteristic of the method strongly. So in general, what we have shown here is so-called semi-implicit Euler.
Formula. This has been the n plus 1 instead of the b.
Yeah, yeah. So the difference of this. No, it doesn't matter. We can. Do you want to check it? Yeah. So the only difference is that okay. So it wasn't the correct one. Maybe in Matlab it doesn't work. No, in Matlab it doesn't work. Yeah. So we can just switch the order of those, yeah, and this provides us the correct semi-implicit method, yeah, that it's typically shown in the literature, yeah. So this is the only difference. And of course, if we change the order here, you have to delete n plus 1 and you have to put n plus 1 here, yeah. So it just changes the order. There is a small difference, yeah. So let's preserve it, yeah. So let's put it aside, yeah. So this is for our method that we have shown, yeah. Let's show the figure, yeah. And this will be for the new method, which is semi-implicit method, which is Euler-Cromer method, which is symplectic method. And now, okay, so can you see the difference? There is small difference. Yeah. So as you can see, the accuracy is the same. So they both solve the system well. Yeah. But the small difference is that let's allow me to zoom it. So let's zoom this part, and let's zoom this part here as well. So as you can see, the difference is that here, firstly, we have analytical and then numerical, and here is other way around. So this is the difference that is caused by the different order, yeah? That we first calculate velocity and then position with updated velocity. And this difference, of course, will shrink as we decrease the time step, but it's present. But it preserves very nicely the overall characteristic of the system. Okay. So this is also called as Euler-Cromer method. Yeah. So in simple terms, it uses this extra information, which makes it accurate. Yeah. And from analytical perspective, if we have analyzed it, instead of having fully explicit method, we have method that have both parts. Yeah, so the first equation is explicit. The second equation is implicit. So that's why it's called semi-implicit method. Yeah, because it's not fully implicit or not fully explicit. Yeah, that's why it's semi-something. Yeah, so semi-implicit method. And typically those kind of symplectic method, it means it's another name as far as I know for semi-implicit methods, yeah, shows far better properties towards those mechanical systems. Okay, despite it's still very simple, yeah. Okay, and I can see that even I prepare some quiz question here. How does the Euler-Cromer method improve the simulation of oscillating system compared to the standard forward Euler method? So, please answer. Just in case.
It says forward method. The forward method uses just n, but the backward method uses n plus 1, which for me is like one more forward.
You're right, but this is simply due to derivation. Yeah. So for the backward method, yeah, you approximate Tn plus Tn using points at Tn and Tn minus 1. Yeah. And when you forward march in time, yeah, when you progress in time with your algorithm, you have only value at Tn plus 1. So you have to calculate Tn. Yeah. And now at Tn you have two values. Yeah. So this is the difference. That you have both point and the value that you want to approximate at Tn. So you're right that that the naming here can be confusing. Yeah. But this comes from this underlying definition of finite difference, that it can be forward or backward. Yeah. So they take the name from there. So this is the reason of this kind of contradiction in terminology. But simply if you do those simple math, but applying those backward difference scheme and forward difference scheme, yeah, and calculate the value of derivative at next time, simply you get for forward scheme explicit integration scheme, and for backward differential scheme implicit integration scheme. Yeah. Okay, because you are pointing here. Could you repeat if Euler-Cromer method is useful for?
We don't use edit oscillating system. That is not useful to work to the basic one.
I think it's rarely used. Oh, okay. In practice, all those methods are rarely used. Yeah. So analyze them to show some overlying principles. Yeah, that explicit schemes looks like that, and they are pretty simple. Implicit scheme, semi-implicit schemes looks like that, and you will deal also a little with more of implicit schemes. But those methods are used only in very specific scenarios. Yeah. So first of all, forward Euler method is pretty universal because it's just general method that can be applied to first order systems. And Euler-Kromer is the method that it can be applied only to second order systems. Yeah, because of how it's arranged. Yeah. So typically it's for general class of mechanical systems. So you can use it, but you use this kind of the methods. Okay, whatever. Yeah. But we use this kind of the methods only to the systems that we have to, in either case, calculate with very small time steps. Yeah. So in practice, when this is not met, yeah, we use higher order systems because despite it works simply better, yeah, it's still first order system, a first order method. Yeah, so its accuracy is limited. Yeah. So the most basic schemes that you might not know, we will discuss it very shortly, is this Runge-Kutta fourth order method. Yeah. So take a look. In forward Euler method, yeah, you use, for example, those 4 steps, and you still have, of course, you are slightly more advanced in time, but this is first order method, yeah. And for Runge-Kutta fourth order, you take 4 steps and get fourth order method, yeah. So it scales much, much better. Of course, it still has some limitations that, especially if the mechanical system is stiff, it still is super slow. Yeah, even this fourth order method. So then you have to have, like multi-step methods to deal with those stiffness phenomena. But this is a slightly different topic. So it has some applications. One very good application are, for example, like that I remember are, for example, car crashes. Yeah, or in a car crash, they use forward Euler method simply because when you have something that happens so rapidly, you will have to integrate with very small time step. Yeah, so when you have to integrate with very small time step because of the physics, then you can use the method like that. Yeah, because getting fourth order will just give you more work. Yeah, but for those pretty slowly moving devices that we often deal with, higher order method are typically better. So yeah, everything has its uses, but yeah, those would be the general principle. Yeah. So why it's interesting, I think that if you have more complicated system, then it won't work so well because simply its accuracy is limited. Yeah, so we can get far better results because of this. Okay, makes sense? Yeah, so typically you would use higher order semi-implicit method, for example. Yeah. Okay, perfect. But let's see. Okay, perfect. It uses higher order approximation of the derivative to reduce error. No, approximation is still first order. Yeah. It uses some extra information to get rid of this error, but okay. Okay, so Helm's method, yeah, I just bring it here to show like another way to get a different scheme, yeah, because there's ton of schemes, yeah. If you have get any word book about ODEs, yeah, there are ton of schemes. This Holmes method, I should check the pronunciation, but yeah, it's second order Runge-Kutta method, RK2, for first order ODEs. Okay, makes sense. So it is generally for first order ODEs, so the ones that are forward Euler is designed for, but it's second order method, yeah? So it means that simply the error decreases to the power of 2 when you shrink the time step, okay? So it converges much faster, yeah? Because with the forward Euler, if you split the time step by 2, you have the method that it's two times more accurate. And here, if you have time step that it's divided by 2, you have the method that is 4 times more accurate. Yeah.
Just for like calculation speeds, does it also mean it takes roughly 2 times as long or like less than 2 times as long?
I think it's roughly 2 times as long.
Basically process speeds.
Yeah, I suppose that's always it's 2 plus something, yeah, because forward order is extremely simple. Yeah, so sometimes you have to have some maybe extra calculation, but almost always, if applicable, yeah, this higher order, just helps with this with speed of calculation. Okay. And by the way, fourth order Runge-Kutta is so famous because it's fourth order and it uses 4 steps. Yeah. And this is the highest order Runge-Kutta method that uses the number of the steps equal to the order. Okay. So as far as I know, it's proven by some clever mathematicians that if you want to have higher order method, you have to use more steps than the order. So for example, if you want to have like, I don't know, 6th order method, you cannot do it with just 6 steps. Yeah, but okay. So there is always limit here, but okay. So just very quickly, if you want to get second order Runge-Kutta, yeah. So this is based on the centered difference approximation. So we had already forward approximation, difference approximation, backward difference approximation. Here we have centered difference approximation. So as you can see here, centered difference approximation approximate the point in the middle by using the points on the both sides. Yeah, so it's Tn plus 1, and we can approximate it at Tn plus half. Okay. Makes sense why it's centered? Yeah. So this is the base for this calculation. Yeah. Error proportional to dt square. Yeah. So this is the reason why it's second order method. I suppose. I hope this point is clear. Yeah. And if we apply this center difference method to our original problem, u prime equal to ftu, we have just that one. Yeah. So we have un plus 1 minus un, just like here by dt. Yeah, so it's simply taken from that, equal to function of tn plus half for un plus half. Yeah. The issue is that of course un plus half is unknown. So we approximate f using arithmetic average of values at tn and tn plus 1. Okay, yeah, you have to do something with this. So we approximate that simply function in the middle is approximated as 1/2 at n and n plus 1. Okay, because we don't really want to know what is in the middle. Yeah, we want to stick to our grid, so to our time steps. Yeah. So if we substitute this here, yeah, then we get that this difference u prime is equal to that equation. Yeah. But again, now we obtain also implicit method, I'm sorry. Yeah, because as you can see, un plus 1 is here and here. Yeah, so method became implicit. Yeah, and Hund's method is explicit. Yeah, so how this is solved? Yeah, so again, but now un plus 1 appears at both sides of equation, resulting in nonlinear equation. Yeah, of course we can solve it. Yeah, but and to deal with this term, we approximate it using forward Euler. It's very, very common. Yeah? If something is that it has this characteristic, yeah, if you can, you apply it forward Euler. Yeah. So simply use this scheme again. The scheme that we want, yeah, it's put here to approximate this term, and then this leads us to the following scheme. Yeah, that u star that came from forward Euler is equal to un plus dt f tn un. Okay. So this is the first step of the method, and it's practically approximation of the UN+1 using forward Euler. Yeah. So the second step is clearly correction to this approximation, and it's second step of this method. Yeah. So this method has two steps. Yeah. And then we can calculate f of Tn+1 with this value because we already have calculated it. This is the same value like here, dt by 2 plus un, and then we get our final value. So as you can see, this step is slightly more complicated than that one, but it's not a big difference. As compared to forward Euler, this method gives smaller error, yeah, because it's second order method, but it also has two stages. However, in case of oscillating system, the Euler-Kromer method is still much better. Okay, yeah. It has just this, because simply those semi-implicit schemes, because they balance, velocity and position, has tendency just to preserve oscillations very well. Okay. Any questions? It does make sense? Yeah. So we use forward Euler and then correct it based on some extra oscillations. Because as you can see, even here, on average, the central difference approximation, looks much better, even when it's further away from this point to the tangent line. Okay. So I think that I have this even implemented here, this Hume's method, or maybe not. Okay, so I suppose that I didn't plan. Oh no, it's here. Yeah. So I will provide it for you if you want. Yeah, but there is. I think that this is application of Hume's method to oscillating system. Yeah. So that's why we have U star and V star. Yeah. And as you can see, we have 4 steps because we apply it to second order system. Yeah, so we have 2 equations for each system and 2 steps for each of those equations. And here is simple demo. You can check it at home. That simply runs this problem that we have run previously, runs it for 10 times, 10 oscillation periods, and plot it. Yeah. So as we are here, let's see. Yeah. Because there was the claim that this method, the Euler-Kromer method, is still better, and as you can see here, yeah, that it for this T0 by 20, it has much smaller error than forward Euler, yeah, because the difference is huge, yeah, because forward Euler already here, gets somewhere out of the context, yeah. So this preserves it much better, but still the error is visible. Okay. And I think that this is pretty practical. That of course there's plenty of those ODEs methods, yeah. And Matlab contains a quite rich library of those ODE solvers, yeah. And here are some of them, yeah. And ODE 45 is, I think, it's still the default method. Yeah, do you know ODE 45? Yeah, so it uses Runge-Kutta fourth and fourth order methods. Yeah, OD15S, it's some backward differential scheme of the order from 1 to 5, and S means that it's applicable to stiff systems. 2, 3, it's simpler method to the stiff systems, and this is also variable order from 1 to 13, but okay. You can read about all of them in documentation. So it's very handy to know how to use OD45, yeah. And their characteristic is that they use adaptive time stepping. Do you know what does it mean, adaptive time stepping? Everybody knows? I should put here some quiz questions about this. But okay, it means, okay, it's written here also. Instead of selecting dt, user gives absolute and relative tolerances with respect to local error estimate, because we don't know the error. Yeah, so the error is estimated. That's why, for example, here we have ODE 4.5. Yeah, so it uses both schemes for fourth order and fifth order. Yeah, because knowing that just intuitively, fourth order method has some accuracy, but fifth order method should be more accurate. Yeah. So knowing the difference between the accuracy of fourth order and fifth order method, we can approximate what is the error, yeah, and then we can keep the error under some tolerance, yeah. And absolute tolerance and relative tolerance is kind of shown here, yeah. That absolute tolerance provide the values of our solution in absolute terms and relative in relative terms, yeah. Nothing super crazy here, yeah. And there is the whole process of how to select adaptively time step to solve it with given accuracy. Okay, it's nice because then we can just design that you, for example, want to get millimeter accuracy or micrometer accuracy, and then you don't have to really fine tune the time step and then check it convergence. So it's very, very handy, yeah. And the basic interface to those methods is like that, yeah, simple, almost very similar to the one that we were using, yeah. So it provides us solution for time and our variables, OD name, OD function, yeah. So we have to provide function that we are integrating, first order function, yeah. So we have to transform it in case of the second order system to first order, like we have done for White Euler. T-span is information about the time step. Because it's adaptive method in practice, we just ask it to report at certain values, yeah. So it will calculate it with internal time step and then approximate it, interpolate, I'm sorry. Yeah, and U0, Y0, as you can guess, is the initial condition that you always need. Okay, so here we have some quizzes, yeah. So now I would like you to try it, to be sure that you know how to use this, yeah. So can you use OD45 to solve those problems? So this is our problem, yeah. So it would be nice if you can use here omega 0 equal to 2, yeah, and then x0 equal to 2, yeah. So then the solution is exactly the same, and you know also the exact solution. If not, I can remind you about this. Yeah, you can also try to adjust solver tolerances. If you don't know how to use it, ask. You can check in Google. You can check because there are for sure many examples. You can check in ChatGPT or whatever. Uh, you can check in documentation. It's extremely popular use case for this method. Yeah, and then maybe later on we'll check the code. Yeah, but please try to solve it for the next 5 minutes. Any questions from the online participants? No, I cannot see any. Is it clear how to solve it to everyone? So of course, yeah, go to documentation, type OD45, yeah. And over here you have some examples, yeah, how to use it for some simple systems. And this system is even simpler than that. Yeah, so let's see how it works. So I'll give you a few minutes and then. Are there any comments from the audience? So were you able to solve the task one? I also know the solution, because u prime equal to u, we have already solved it. Yeah. So like this population growth, it simply translates to this exponential functions. Yeah. And the second one is our oscillating system. So despite that, do you want me to solve this quickly? Okay, yeah, no. Okay. So let's solve it. Okay, hands on all the okay, so let's write two sections here. Okay, so this is problem definition, u prime equal to u. So here is Matlab's help, yeah, and we will use this ty equal to OD45, OD1, t-span, and y0. Yeah. So ty, of course, is our solution. OD45 is function that we are calling, and we need those stuff. Yeah. So first is OD1. Yeah. What is OD1? Yeah. OD1, according to help, is function handle that provides dt dy over dt. Yeah. So it's function handle that provides this dy dt. So y prime. Yeah. So it's our function that we use already for forward Euler and all the other methods. Yeah. So it's function handle that accepts t and y. So we are using u, yeah, and it returns u prime, y prime, or we transform it to u prime, yeah. So in our case, u prime is equal to u, so it returns u. So it's other function. No action, yeah, simple like that. Make sense? Now is t-span. What is t-span? Yeah. So the next one is a vector. That you can provide must be a two-element vector, or it can contain more. Yeah, but we will just use this simple formula for two-element vector from t0 to t final. Yeah, so we will provide from 0 to, let's say, 5 seconds. Okay, or even 1. Let's do it. Start with 1. And y0 is, of course, our u0, so it's equal to 2. Okay. To see what is happening with Matlab, let's just run it. Okay, we ran this section and we got some solution with 41 steps. Yeah. Oh, let's just plot it. because we had here some plots, yeah. So we get solution like that. Okay, so this is solution, how to solve it. Yeah. Do you have any questions to this?
Doesn't work.
What is not working?
Yes, like a vector link for one.
But you have y. Y is unknown. You have to do or y here. But then it should work. Yeah. Okay. Yeah, it's always better to try by your own. So use the 45 for harmonic oscillator, yeah. So okay, so we had here it. So we don't need dt in practice. We can solve it for 10 T0 to see how it works, because we have seen that for this Runge-Kutta second method, Holmes method, it's shown some excessive oscillations already. So let's see how it works with default parameters, yeah? So of course, the calling scheme will be the same, yeah? The plotting will be slightly different, but because we have second order system. So we have to define other fun with ty, yeah? And now the first variable is our u, which is position, and the second one is our v, which is velocity. Yeah? So we have already done it here, for example, yeah. Before we change the order, that of course u, the run hand side is just v, yeah. So here for the first, which is u, the solution will be y of 2, yeah. Because simply we have that our y is equal to uv, yeah. So what we need is y prime is equal to, of course, u prime v prime, yeah, which is simply equal to u prime is v, yeah, and v prime was minus omega 0 squared times u. Was it the case? Minus omega 0 u. Yeah, exactly. So we have to implement it, yeah. So this is our v, yeah, because v is simply y of 2, yeah, and our second solution will be that one. Here, minus omega 0 squared times u, and of course u doesn't exist in this context, and u is simply y of 1. Yeah. Then we have to define y0, which is of course, if we have u0 equal to 2 and v0 equal to 0, we have y0 equal simply to u0 v0. Okay, And let's check if it's yeah. The task was solved, which is nice and promising. So the task was solved, yeah, and let's plot it. So now you can see that y0 is of course vector with two values, and the same applies to y, yeah. So y is now a matrix that contains two columns, and of course I hope that you can guess that the first columns corresponds to the first element, so this is position, yeah, and the second columns correspond to the velocity of the system. Okay. So now, in order to plot position, okay, we have to plot T, U, all the elements from the first column. Yeah. Yeah, exactly. Something is not correct. Okay, because integrate to one. Yeah, so yeah, that's true. Because it looks a little surprising. So that's true that we haven't defined T-span here. T-span is equal to 0 and TK. Yeah. Yeah, and now it's much better. So as you can see here, even with the default tolerances, we do not have any excessive oscillations. Yeah. So it preserves the characteristic of the system really, really nicely. So all the 45, even with default parameters, works pretty fine. It uses like 300 steps, yeah, but it's not super excessive. Of course, it starts with the very fine time step because of the characteristic of this adaptive method, but then it became far more coarser. Then what else we can do? We can also compare it with exact solution that we have here. Just to see. And then we can copy paste all this plotting. And of course, here we have I change it to have dashed line, yeah, and yeah. So as you can see here, you cannot really see a difference between the numerical and analytical solution at this resolution, yeah. So let's zoom it, and let's zoom it for the final part because typically it's the case that even when here it looks okay, and the final part it starts to diverge. So we can see some differences, yeah, of course, but well, they are at the level of quite small differences, yeah. And when we restore it, you cannot see. So the method it's really accurate and works really nice for our system. Okay, so this is the solution for this hands-on. Is there anything surprising here or unclear? Any questions? Oh, okay, perfect. Then we have last question for this series. Why is Matlab's OD45 function commonly used for solving ordinary differential equations? And what type of method does it use? Yeah, it will be recorded.
No, it's. It's okay. That's not like zero here. And I'm not see just over here. Just I think. But I think that's your happens better. Six. And down. Now we'll just run this section. Now run just this section. And this. As you can see here, we are not involved position and velocity. So that one has was the second one is velocity. 3 plus. 1 is number. Now we will still take that. Yeah, so okay, so
Again, with programming, it shows that practice is very important because when you write 3 lines of code, most likely you already have error there. And so, yeah, that are just, kind of unexpected. Okay. Nice. It's nice always when most students get the correct answer. Okay, so we can finish this activity. And here, if you really want, you can see the fourth order method, yeah. Fourth order Runge-Kutta method, yeah. You can derive it, of course, yeah. So this is the method that is behind mostly this all the 45 lets we discussed. It use 4 stages, but yeah, it's very nice method. Yeah. So we really, won't get maybe into exactly how to get it done. Yeah. But as you can see, it starts with quite a different scheme, yeah. So it starts with acknowledging that, to get the solution, between those 2 points, you can integrate this in time, yeah. And then instead of using any kind of specific this, so it doesn't start in the way that it uses some even higher order approximation to approximate the derivative. It rather tries to integrate it using Simpson's rule, yeah. And the Simpsons rules has then the factor for function at this time, some 4 factors in the middle, yeah, and then function at the next time, yeah, and it tries to approximate this tree with different schemes using forward Euler and some other methods, yeah. So I have it here, but I think then if you want, you can follow it, but as you can see, it uses forward Euler, backward Euler, and even central difference approximation. So it just puts even more elements of the puzzle to the game to end up with all this. And it's still a fully explicit method that has, that is fourth order accuracy, which is extremely nice. Yeah. And of course, there is a large family of implicit Runge-Kutta methods as well. Yeah. Yeah, and many, many others. There's plenty of them. Okay. Any questions to all these? Yeah. And here is the next set of assignments. Yeah, just similar scheme. Yeah. So 3 tasks from the book: report, PDF, zip. Make it looks nice and read well. And that's all. Okay. Any questions? We still have half an hour, yeah, so maybe we can go to solving nonlinear equations. Okay, are you ready to the shift? Do you need 5-minute break? Because, okay, now it came with some theory. So we were solving now differential equations, yeah, by using ODEs. And now we get back to solving algebraic equations, but simply nonlinear ones, yeah. So we want to find a solution to the equation in general form f of x equal to 0. And of course, in practice, yeah, it's not so trivial, yeah. So here's the example, yeah, if we have some, sines, cosines, and exponents, yeah, and then we want to find the solution where this is equal, and of course, then we can always put it on one hand side and form f of x, yeah. It's not extremely trivial to solve it, just by looking on it, yeah. And as typical, because we are in the domain of the numerical methods, we want to find some approximate solution rather than exact one here, yeah, like with all the others methods, yeah. So try to find some tricks to solve it, yeah. The problem is also good root finding, yeah, simply because we are finding the roots of general functions, so where it crosses 0 or it touches 0. And some areas are, as we have seen, implicit ODEs. Yeah, so we haven't solved go with implicit ODEs, but if we have implicit ODEs and this kind of the methods, then we can implement them. Optimization, finding the minimum of a function, is another big area, and of course, kinematic analysis of mechanisms, which will be one of our next topics. Is it clear? Any questions? Make sense? Yeah. And we will discuss like 2 methods of how to. Yeah. So how would you solve it? Any ideas how to solve it? This kind of general function using computer? Yeah, of course you can use solver. Yeah, but assume that you are just we what algorithm? Yeah, in general term. Of course, with Matlab you use something like F0 or Fsolve. Yeah, and then then run it. Yeah, but there is some algorithm behind. Yeah. So what can be very simple algorithm to do it? Maybe you have heard about them if you have any kind of numerical methods courses. Yeah, yeah, there is. Yeah, of course. Yeah, but it's already advanced technique, and it has some limitations. But yeah, we will for sure discuss about Newton method. But okay, we have some quiz here. So okay, now what is general form of the problem when solving nonlinear equations as shown in the slide? Yeah, just a second ago, and what is this process commonly called? At least I remember that the method that I have used was, for example, bisection method. to find roots. Have you ever heard about this? Maybe. Yeah, probably, yeah. Some ages ago. Okay, okay. Yeah, but okay, let's give like 10, 20 seconds and let's see. Okay, no, it's not called optimization. Yeah, optimization is just some range of problems that you can solve using this root finding method. But okay. Okay, so we will start even with the most basic one, with the simple brute force method, yeah? And our aim is to go with Newton's method, and especially for the Newton's method for multiple equations, because we need it for solving kinematic equations. Okay, but brute force method, as the name suggests, it just use sheer power of the computer, yeah? So the idea is very simple, yeah? So it's almost like on the plotting, yeah. So based on the collection of the points, yeah, that we use, for example, when we make plots, simply go through all the points and check when function crosses axis. Okay, so you just have a function divided in 10,000 points, yeah, and then check, where when it appears that just values goes from negative to positive or other way around, yeah. Uh, this requires a lot of computation typically, therefore the name brute force. Yeah, for our simple function like that, it's not a big deal. Matlab or whatever system will do it in very quickly. Yeah, of course the problem starts when we have complicated functions, but this is typically the case. But it should be easy to implement. Yeah, because I hope that you understand the algorithm. You just divide it and then go point by point and check it. So here's how the algorithm could look like. We have a set of points, xi, yi, yeah. So on both axes, yeah, of yi equal to our function, yeah, and I, yeah. So again, we create this kind of grid with most likely equally spaced points, yeah, xi, yeah. We put them on the axis using something like this line space, then calculate y. And curve crosses x-axis when yi and yi plus 1 have different signs. Yeah? So simply we have yi and yi plus 1 smaller equal to 0. In case that some of those ones hit 0. Yeah. And that is, that fx is somewhere in this, in there. Yeah. And then I believe that you have one task that was involved with linear interpolation, yeah. So assuming linear variation in the interval, because what else we can do if we use a large enough number of the points, yeah. The root is located here. So this is simply linear interpolation, yeah. When you get some root that is very quickly, yeah, to get it, some nice approximation, yeah. And it's very typical to use it, yeah. Okay, let's take a look on the implementation. So it should be somewhere here, and brute force root finder. Okay, so this is our algorithm, yeah. So it returns all the roots, brute force root finder. F, as you can guess, is function that it takes. A and B are from where to where search, yeah, because we have to define those intervals. We cannot, search for the whole axis like that. And N is the number of divisions, yeah. So we can generate x points. Then, assuming that our function is vectorized, we calculate y points. Then we assign the vector that will hold all our roots. Yeah, so x points where the root is located. And then we just go through all the points. Yeah. So we will run this for loop from 1 to n minus 1 because we are checking 2 points. Yeah, so we have to cut on at one of the ends. And then we check that if there is change in the sign, we apply equation from the slide to calculate the value of the root. Yeah. So it's exactly that equation, yeah, to calculate the value of the root. We add it to the list of the roots, and then we return it. Simple. Any questions? It can be done, of course, in 1,000 ways, yeah. But and then let's take a look on demo. So it searches for the roots. If not empty, then it displays a number of the roots and then plots them. Or if there is no roots, it says that it wasn't able to find any roots. Yeah. So we have the function x minus x squared times cosine 20x. Why not? And then from A to B with 1,001 points. Yeah. So let's run this code. I wonder. Okay. Now it works. So this is our function. Yeah. And those are our roots. Here with the dots. Okay, it works. I wonder if we should dig into it. Yeah, if you are interested. Because the issue with the code that we have here, let's close all this stuff. That here we get one warning from the Matlab. The variable appears to change size on every looping direction. Consider paragraphing for speed. Yeah. Do you understand what is this talking about?
Every single time.
Yeah. Yeah, and Matlab somehow, handles it this type of the behavior in an efficient way. So the question is if you want to want to solve this, yeah, this problem, yeah. So the command relocates roots vector at each occurrence, yeah. So we have to allocate new memory, copy it, and discard the old one. Matlab warns this slows down the program. Can we avoid this? So yeah, so one question, can we avoid this? We can always avoid this. Yeah. So how to avoid this here? In C++, you wouldn't have this issue because you would no, yeah, you would just declare a vector, and of course you can handle it by hand, yeah. But in C++, you can use simply standard vector, and then it's solved by you because it allocates memory in more efficient way than here Matlab does. I don't understand why Matlab doesn't do this.
As a pushback.
I don't know. Yeah, maybe they have changed, of course. Yeah, so maybe it's already pointless. But the last time I haven't. Yeah, but how to make it manually? Yeah, because here the issue is that as you can see, because of the character of this problem, we don't know how many elements we'll have in the roots. Because we can have from 0 to thousands of roots or whatever, yeah, is the number of the roots. Yeah, we can have really many of them. Like here we have, in our example, we had already like 20, I believe, 25. Yeah. So how to pre-allocate stuff like that? to work. You know how to do this? It's a little tedious.
Just assign into the like there n and then n+1 and then it is the point where it has their
The calculator and then we return it. Yeah, this is one solution. Yeah, of course. Yeah, it could be done that way. Yeah, there is always complaint that it wastes memory from other side of the hand. Yeah, so because then you allocate a lot of it. I will show you what is the kind of good solution. Yeah, but we won't dig into it too much. Yeah, because your one is valid, of course, but yeah, there is always this claim that when you have million of points, then it can get out of the range. Yeah, here with small numbers, it doesn't really matter. Yeah, so I will show you how it's done typically and how it's done also with this C++ vector and in many other solutions. I hope that I have it here. No, I don't have this code here. My bad. Or maybe no, it must be here. Okay, it's here. Yeah. No, it's here. Perfect. So it's to say at least a little annoying that it's not there because as you can see, if you compare simply brute force method, yeah, and that brute force method with prior allocation, you can see that it almost doubled the size of it just to solve this issue. So it should be hidden somewhere, yeah, not like here, yeah, because the way to do this is to assume that we will have some number of the roots of solutions, yeah, then allocate those number of solutions. But of course, it can happen that you will have more solutions that you predict, and it happens pretty often, yeah. So then, when it happens that you have more solutions, then you double the size of your allocation, set new Rmax, and continue as such, yeah. And of course, at the end, you have to cut the size of this allocation, not to return the values that weren't there. Okay? So it would work that way that, for example, like here we have 10, but we return 25, yeah? So it will go and go, yeah? So firstly, it allocate space for 10. So we'll add first 10 without any issues, yeah? But when it will like to add 11th, yeah, it will allocate the space for 20, yeah, and use the old one. And then we'll continue adding. And when it hits 20, it will allocate the space for 40, yeah. And then, of course, we'll get to 25, not reaching 40. So at the end, we'll cut from 1 to 25, yeah. So kind of advantage is that instead of pre-allocating 25 or 6 times, yeah, whatever is the index, more like 24 times pre-allocating, yeah, here we'll allocate it like 3 times, yeah. So this is the saving that this number of this allocation is much smaller, yeah. But the code is, to say the least, not very welcoming, yeah. So for small cases, I wouldn't do this. So this is because, yeah.
Attribute test, if it's at that point not simply better to simply say R max equals to the size of X.
Yeah, well, yeah, it could be. Yeah, it depends. Yeah, but this is just typically how it's done in many languages as universal solution that works for any kind of n. Yeah, so if you provide here million and still have 20 roots, yeah, we don't have to allocate another array of the size of million. Yeah, but okay. So so we should even, so one solution is here, yeah, and we should use time it to see even if this makes sense, yeah. So let's time the solution, okay? Because I cannot see code here for this, so let's write a script, yeah. Okay, so as it's written here, time the code to check if this makes sense at all. Yeah, we can use time it function. Yeah, and time it, as you will check, it's measure time required to run function. Yeah. Why there is special function for this? Simply because, many of those functions takes some nanoseconds to run or milliseconds, yeah? And if you run it because of the noise of whatever it is at your computer, it's totally unreliable to get this number, yeah? So the functions like time it, yeah? Check that your run takes milliseconds, run it like 10,000 times and provide you, for example, mean value of the mean value of average of your run, okay? Yeah, so because yeah, typically you can do it by yourself, run it in the loop 1,000 times, but well, it's better to have function like that, yeah. So, and as you can see, the call is pretty different. T is equal to time it of f, and f is our function, yeah. So we'll time it twice, yeah. So we want to, so we will get this demo. So we need some function and some solutions, yeah. Because of course we can use it with TikTok and the loop, but we will use time it for that. So maybe that's why it's not the code here, yeah. So this is how it works, yeah. So we will get f time 1. So we need a function. So we define the first function. And you can check that this function, cannot return anything. Yeah, it means that, it cannot accept any arguments. So you have to just use it like here, yeah. Because, it's the function for timing. It's not function for iterating or whatever, yeah. So, it doesn't make sense that just require function just to run, yeah, not to take any arguments. So this will be the first function. Then we have f time 2, which will be root finder pre-allocate, yeah, with the same setting. And then you can just run it. T1 equal to time it f time 1, and T2 equal to time it f time 2. Yeah. And I will just display it. Yeah. And let's see. It typically takes a few seconds. So as you can see, in modern Matlab, this kind of manual pre-allocation decreases performance. It's the first time for me in this course to happens, but yeah, I'm, in programming, nothing is sure, yeah, because the whole ecosystem changes, yeah. So now you can see that, they have left this warning to pre-allocate, so we pre-allocated according to our best knowledge, and we get the worst results. So let's run it again. Okay. So after the second run, we get some changes. Yeah. So this code start to be slightly faster. Yeah. Can you guess what? Because you can see that here we have the run time 10 to minus 3. Here we have runtime 10 to minus 4. And here this is slower, and here this is faster. Yeah. Any idea why this is the case?
Fixes it probably took some things on workspace and just already had allocated things that could just write over. Didn't need to know access to you. Memory again.
I doubt. I think that it makes it on. It doesn't run it on the workspace. Yeah, run it in its own context. Yeah, but I think that this is because of the just-in-time compilation. Yeah, Do you know what is just-in-time compilation? Okay, yeah. So I suppose that because of the just-in-time compilation, simply this takes more time because this function is longer. Yeah. And that's why, and also, as you can see here, is clear indication that, just-in-time compilation takes a lot. I'm super surprised that timing function doesn't take out of this compilation time because we are not interested in compilation time. We are interested in runtime, yeah. And here, this is faster because despite everything, still, fewer allocations provide us faster code. So let's run it again. Yeah. So now I would expect that it will be more similar to that one than to this one. Yeah. Because if we want to get this result, we have to clear the cache for just-in-time compiler. Yeah. So the range is similar. It gets even faster. Yeah. So as now we start getting more consistent results, 0.3 millisecond, yeah, and 0.2 milliseconds. So this is slightly faster, but the fuss about this code is quite high, and the difference in performances. Okay.
To create a workspace. Just run.
Sorry?
Could you create a workspace and then type it again?
Yeah, of course. You mean like that?
Yeah.
No difference. Now I could use clear all. So this is the reason why clear all is harmful, yeah, because it clears also GIT logs as far as I know, yeah. So now when we clear all, we clear, plenty of the stuff, and now when we run, you can see how longer it takes because it has to compile everything, then runs this, yeah. So that's why you can see the influence of GIT here in the real time and harmfulness of clear all using just everywhere, yeah. So you are slowing your code tremendously because all this get compiled, yeah. You could see it took a few seconds, yeah, and now all the rest calls takes like that, yeah. And despite still, it's yeah, yeah. I don't know why this is so underrepresentative, but okay. Another magic happens there. Yeah. Okay, okay, and we have some quiz. Then we are ending in a few minutes. What is the main characteristic of the brute force method for finding the roots of a function and why it is called brute force?
I believe that the reason why the number goes lower, the more times you press it, is because the CPU allocates more for the process. But if you just run it in random intervals, it will keep showing different size.
Yeah, no, but it was other way around. When I start running it many times, it starts to be more consistent. When I run it, infrequently, it shows different results. So here, this one was much slower, not even on those numbers, but simply much slower because of the just-in-time compilation. Yeah, but execution time is so. I suppose that it has something with execution prediction on your processor. So
When you see it, like if you have like one program open, it can focus on this one, but if you have browser and other things open, like you have your process streaming,
yeah, that's true.
so it constantly
Yeah.
changes.
Yeah, but it's like many cores, but of course, it's all this affects. Yeah, it would be much better to benchmark this on a freshly run computer at least, yeah, or maybe even some dedicated machine, and you are right, yeah. And also simply by running the same code, I believe that processor can optimize this run, and it's adapted to it. So there are some super fancy things going on, to make it faster, yeah. But it also shows that, as they claim, now there is less and less need for code optimization by yourself. Yeah. Yes, it is.
Scale this up. It could take a bit.
But do you know where will be the issue if you scale this up? So this is always the problem, yeah. So first of all, if you scale this up, you don't go with Matlab. If you scale it up to center range, yeah. So if you stay with Matlab, yeah, maybe you can sacrifice it, yeah. And even then, where is the problem? And will you run this one time or 10,000 times? It makes a difference, yeah. And just use better algorithm. So there are many solutions. So practice shows that people tends to optimize the code, yeah, far often than it's needed, and then they often miss the point. Okay, but we had this quiz. Let's see. Wow, nice, perfect. So at least we have 15 active students, which is nice. Okay, let's go. Any questions? So we just show it for those like educational purposes. Don't do this until you really know what you're doing. Because I have to remove it, I suppose, yeah, because it was super relevant when I started this course, yeah, because then the difference was like few times, yeah, when you have larger calls. But now with GIT and other, it start to be less and less, yeah. So all this decreases. So really, okay. Newton-Raphson method. Yeah. Okay. So we skip all those range like bisection method and others. Yeah. We get directly to Newton-Raphson method. Yeah. Because we will use it practically. Yeah. It shows totally different approach. Yeah. To it. It's pretty famous and really widely used in practice. Yeah. Because it's super fast. But it has one issue. It does not guarantee that a solution will be found. Okay. So why it's used? Yeah, this method is used in scenarios when you have solution and you are somewhere here typically. Of course, when function behaves well, yeah, like this one, is not an issue. Yeah, but let's assume that here you look for the solution, but you end up here. Yeah, you can end up here because of different algorithm. Yeah, for example, I would guess that some of those Matlab methods could work that way, that they firstly try to get using some kind of bisection or whatever, some searching, yeah. They get pretty close, yeah, and then to close the final gap, that can use Newton-Raphson, yeah, because the Newton-Raphson just can rapidly achieve the solution with very high accuracy. Okay. In our case of mechanical systems, we will always get pretty close, yeah. And then when we march in time, we still will be pretty close, yeah. So those system fortunately behaves pretty nicely. So we don't have to go there, yeah. Idea is to construct series of linear equations, as we know how to solve them nicely. So, yeah, so we will just put lines there, like always. Yeah, the same we do with ODEs. Yeah, we try to find some lines that are approximation of tangents, and expect they will bring us to the solution of a nonlinear one. Yeah. So in practice, again, it will be trick with tangents. Yeah. So we will have some points here, put a tangent, find another point, put a tangent, find another point. And tangent is linear stuff, yeah? So we will test function f of x equal to x squared minus 9, like that, on interval of from 0 to 1000, yeah? So x0 is our initial guess, let's say at 1000. Again, this function behaves very nicely, so even that we are super far, yeah, we will get the solution. And at least, being far, we can make few of those iterations, and you can see how it progress quickly. Yeah. So the solution is of course 3. Yeah. And as you can see that from 1000, then we halve the distance. Then we again halve the distance, and so and so. Yeah. Next, we approximate the function at the point with tangent line, this green line, and we solve this. So and we solve this line and go to x1 and continue until we reach tolerance. Because yeah, kind of issue with this method. Okay, so this is the equation that we are using. Yeah. So of course, then we know that the tangent line is f of x equal to 0, value of the function, plus f prime of x. So here you can see already that it requires derivative of the function to be computed. Yeah. There are modified Newton method that can use the same trick like we use, so like some second method. Yeah. But then efficiency drops quite a bit. But the original one requires to have a derivative of the function. F prime of x, x minus x0, which x is this point, and we try to find it. So x equal to x0 minus, and this is equation. Yeah. So very simple derivation of the method. And this is the new candidate plot x. Yeah. And we progress like that. Make sense? Yeah. Oh, and here was some question. Damn, it is, I go those quizzes one ahead of time. Yeah, I should remove it. But okay, it's here, so it will be so nice to answer it. Why is parallel caching important to work with vectors in Matlab? But as you could see, our colleague discussion, yeah, I really wonder if this is so important.
It comes support that you have like really large vectors and your RAM is like.
Yeah, for sure. Yeah.
And yeah, currently we have so
Yeah.
much RAM in comparison to what
Yeah.
we use.
Yeah. Yeah. Well, it's much easier to make allocation when you know the number of the solutions. Yeah, that when you don't have to do this kind of the tricks, but you can just, because we pre-allocate pretty often. Yeah, like for example, why implementing even those OD methods. Yeah, we pre-allocate the solution, but then pre-allocation is just single one line. Yeah, so then I think that then it's rather far better to pre-allocate than not. Yeah. Because even with those simple example for forward Euler, if we want to allocate, we have to, for example, make like this 10,000 allocations. Yeah. Then I think that the effect will be high. Yeah. But it's super easy to pre-allocate. Yeah. But like here in those moderate sizes, and then you have the code that it's twice as large. Yeah. I wouldn't bother. But you are right that it's strongly about the case. Yeah. So when the pre-allocation is easy, I think it's much better to use it using those zeros. Okay. Let's give few extra seconds, yeah.
Come across any.
Okay, perfect.
Come across any like project that actually use like more than 8 gigabytes of RAM during a simulation. Like a program like this.
It's not so complicated. Especially if you have finite element code, then you can go out of the limits. In mechanical system, it's not so often, yeah. Because in mechanical system, typically the issue is not with the RAM. The computations are highly nonlinear, and there are many of them. And the other characteristic is that typically it's hard to even parallelize the solution, because it's plenty of small operations. Yeah. But when you have the problems like, like particle dynamics, then, just your RAM is your limit. Yeah, because, the more, the better, typically, yeah, the RAM and resources. So with simulation, certain areas of simulation, it's super easy to use whatever RAM you have. With mechanical systems, you can reach this, when you have some tasks that require a lot of parallel simulations. Yeah. So if you have some predictive algorithms, yeah, like okay, we have to end very soon. Yeah. Okay, so we already solved the results. So maybe just solve this last quiz and then we can go home. With you. There are solutions like, for example, we are working with Isaac Jim, and then you can run on GPU, for example, 10,000 of robots at once or machines. Then you use quite a lot of RAM. And then typically this number like 8, 10,000 depends on the number of RAM and available cores. But I think it's still more about the cores because typically, but those graphic cards has, like 20 gigabytes of RAM. And why to have 10,000? For machine learning control algorithms, typically.
How much then do you still try to make it efficient, like memory usage? Or do you just still say like memory usage efficiency is second to just running it?
It depends on the problem. Yeah. I never bother with RAM. But I suppose that, guys that are into finite element method can bother with it much more when they really solve some large scale issues. Yeah. But then they use the techniques like, to put your matrices on disk to solve them. They are so huge. Yeah. But then, of course, efficiency of the solution drops rapidly. But there are ways to overcome it. But okay. But I think that, we'll stop here. We discussed how the Newton-Raphson method works, more or less. Yeah. So the next time we will meet, so most likely in about a month or next week. I wonder what would be better. Yeah. Because, but let's see how it will go with the range. We cannot meet in 1 month. Yeah. Okay, let's see how it will be arranged. Yeah, because I remember they have one visit that it's around this time. Yeah, so I will let you know who will come next time. Yeah, so either I will go be here next time, and then Alexander will come two next times. Yeah, so one before this autumn break and one after this autumn break, or he will come the two next times, yeah, consecutive times, and I will come after the autumn break. Okay. But yeah. So I'll let you know how to end up. Yeah. Both solutions are kind of nice. Yeah. I would prefer to maybe to be here next time, despite everything, finalize this topic, and for him to close this topic with the next two classes. Yeah. So I'll try to arrange this that way. Okay. Perfect. Any questions? Okay. Online, nobody speaks up, so I suppose there is no questions. So thank you. I will share with everything, and there is nothing in the chat. Yeah, and we'll see most likely in a week. If not, I will let you know. Okay, have a great weekend. See you.